So let's take a look at the Socrative app questions as we came in here today and see how we did. Question number 1 says, without looking at a table of atomic or ionic radii, which of the following isoelectronic species would have the largest radius? And what does isoelectronic mean? Same number of electrons, which means they have the same electron configuration. They have the same electron configuration. So same number of electrons, same electron configuration. So checking these out, the sulfide ion would be the one that has the largest radius. And what would be the second largest? Chloride, followed by potassium ions, followed by calcium ions. Exactly. So if you were to put them in here again in descending order, sulfide's the largest, followed by chloride, followed by potassium ions, followed by calcium ions. Any questions on this arrangement? Okay, question number 2. What is the electron configuration of the antimony ion? That's the antimony 3 ion. Checking this out. Correct choice is C. Any questions on this one? All right, next up, number 3, ionic bonds are found in all of the, or which of the following substances? Select all of the answers that apply. Correct choices here, A, B, and E. Why would C and D not be considered ionic compounds or having ionic bonds? They share electrons because in each case they are comprised only of nonmetals. So when we have metals to nonmetals, we have ionic bonds. When we have nonmetals to nonmetals, we have covalent bonds. Then the last one, covalent bonds are found in which of the following substances? Select all the answers that apply. Remember that if metalloids are present, then we also have, if it's metalloid to metalloid or metalloid to nonmetal, we could also have covalent bonds present. So any questions on these? All right. Quick reminder here that tomorrow is the last day to withdraw from this course. If you're concerned about your status in this course, please talk to me. We did mention last time that there is an ACS final exam study guide that's available at the reference desk in the library. Anybody happen to check that out? See if I'm lying. Is it there? Okay. It is a full, and it is a reference desk. Okay. So it's at the reference desk. As I mentioned last time, it is a full year study guide, which means it covers concepts from the full year. Because there is such a thing as a full year ACS exam, we only give the 1 semester exam here. And if you take Chem 2, we take a 2nd semester exam. We do not take the full year exam at this college because we have some people that transfer in here for the 2nd semester, blah, blah, blah. So just make sure that when you look at it that you're looking at the 1st semester topics. All right. Today we are going to talk about bonding and the 2 types of bonds, which we already saw on the Socrative app quiz. They were covalent bonds and ionic bonds. And so we're going to look at these. And there's also another type of bond that we've probably not talked about much in here, and probably in your previous experience chemistry you've not talked about it much either. And that is what's called a metallic bond. And what are some characteristics of substances that have ionic bonds? Right, between metals and nonmetals. What is another characteristic? Electrons are given, or we would say that they are transferred. Exactly. So electrons may be transferred from metals to nonmetals. So that's the main distinction. Covalent bonds, these are between nonmetals, or which other elements? Metalloids, right? And in this case, we say that electrons are shared. Now, metallic bonds. What these are is we say that metallic bonds, these represent metal ions in what's called a sea of electrons. And that's actually the way that we find metals. Metals aren't neutral atoms. It turns out that one of the reasons why metals are very good conductors of electricity is because they hold those valence electrons very loosely, and those electrons then can travel easily up and down a wire or whatever else. So again, we look at metallic bonds as being metal ions in a sea of electrons. Now, we're going to start here today by looking at ionic bonds. And when we look at ionic bonds, we'll start first of all by looking at these elements. Let's look at sodium and chlorine. And start by writing out their Lewis diagram. So if you have your periodic table handy, you might as well get it out. We'll be using them. And another copy. All right. Anybody else? Never have too many. All right. So if we want to write out the Lewis diagram for a sodium atom, how many dots did we show in a Lewis diagram for sodium? And for chlorine, how many? And how do we get that for chlorine, the 7? It's in group 7A. And so the Roman numeral there tells us how many valence electrons that element would have. So we put in the 7 valence electrons for the chlorine. We then go from the neutral atoms to the ions. And if we now want to go and form a sodium ion, sodium ions have a charge of how much? 1 plus, okay? So if we have a charge of 1 plus, what does that mean has happened to the valence electrons? We gained or lost electrons? We lost. So since sodium has 1 valence electron, it loses that 1 valence electron. This is how we write a Lewis symbol for a sodium ion. So we still do have the 8 valence electrons that are present in the shell below, but when we write it with 0 valence electrons like this, that's representing the same thing as saying it has a full outer shell. It's just the outer shell that is below the valence shell that has been removed. Okay, charge in the chloride ion is how much? 1 minus. So if this is 1 minus, we're going to write the Lewis symbol for the chloride ion. Charge of 1 minus means what has happened? It's gained 1 electron, exactly. So we'd write the Lewis symbol for the chloride ion like this. And then what we do is we add on some square brackets and show the charge outside. And so again, this here is the representation of a sodium ion. Typically for metal ions, we show them void of valence electrons. That is, we show them having been removed. In the case of nonmetal ions, we tend to show them as having completed that outer shell. And then we place the square brackets around the charge outside. Explanation I recall having heard is that very often when we write these charges, we don't want this sign to be confused with any dots that are here in the symbol. Now that said, if you go on to Mastering Chemistry and you're asked to draw out the Lewis diagrams for the ions, on Mastering Chemistry does not have the ability to draw the square brackets and would write them like this. But it is the correct protocol to write them with the square brackets. And if you look in your text, you'll see that's how it's done. You will want to be sure that you include those square brackets. Any questions? All right, so if we then wanted to write a Lewis diagram for sodium chloride, a Lewis diagram for sodium chloride would be quite simple. All we'd do here is something like this, and we'd say that this here represents that Lewis symbol for sodium chloride right here. So the one sodium ion and the one chloride ion. Now, if we want to go on to something like sodium and nitrogen, we want to write out its Lewis symbol. Let's go ahead and see how this would be done and how we might determine the formula. So to do it for this one, we start with sodium. How many valence electrons will the sodium have? And if we go to nitrogen, how many valence electrons on the nitrogen? I hear 5, I hear 6. How many is it? 5, because it's in group 5A. It means it has 5 valence electrons. So we put in, where do I have them? Right here. 1, 2, 3, 4, 5. Now, in order to satisfy what we call the octet rule, we haven't used that name yet. We're going to start using it here right now. The octet rule is what dictates how atoms bond to each other. And what the octet rule is a strive or desire to wind up with 8 valence electrons. Because it happens to be something stable about that arrangement, because of course we find out that the noble gases here have the 8 valence electrons, and they tend to be stable as well. Sometimes we refer to the octet rule as the noble gas configuration. So again, sometimes we refer to it as noble gas configuration. And that's probably more accurate because, of course, if elements try to bond with each other, sometimes they will try to wind up having the configuration of helium. Of course, never has an octet. Its outer level is filled with just 2 valence electrons. So your text does, however, use the term octet rule, but it does also, in most places, refer to it as the noble gas configuration as well. So if we come back to this one and we want to attain that noble gas configuration, the element that's going to lose electrons is going to be sodium. So if we want to show sodium giving up its valence electron to the nitrogen, we could. Of course, once sodium gives up its valence electron, the sodium atom forms a charge of 1 plus. The nitrogen, on the other hand, at this point only has 6 valence electrons and still needs 2 more. So what would be the best way to get 2 more valence electrons? Put in more sodiums. And how many more sodiums? 2 more. And so each one of these sodiums would come with their valence electron, would transfer 1 here, transfer another 1 here. And of course, because each of these sodium atoms has lost 1 electron, they acquire a single positive charge. Because the nitrogen has gained 3 electrons, the charge on this nitrogen becomes a, how much? 3 minus. So this is why, back when we were going through nomenclature, why the sum of the positives had to be offset by the sum of the negatives for the anions. And in the end, if you were asked to write the Lewis diagram for the sodium nitride, it would look something like this. I was just placing the colors in there just so we kind of do an accounting and keep track of where those electrons came from. But again, this is what it looks like at the end. Therefore, if we go back, you might remember that everything here in group 15, if it was a anion, would have had a charge of 3 negative, because these elements were always gaining 3 electrons. The elements of group 6A would always have a charge of 2 negative because they would always be gaining 2 electrons. Everything here in group 17 would have a charge of 1 negative because they were gaining 1 electron. Likewise here, everything in group 1A would have a charge of 1 plus because these would always lose 1 electron. These here would always have a charge of 2 plus because these would always be losing 2 electrons. Now, something ambiguous kind of happens in here because remember that these are ones that have multiple charges. Typically, when it comes to writing out Lewis diagrams for ionic compounds, we don't pay much attention to the transition elements because in many cases, they lose more electrons than just the valency electrons. As we looked at in here last week, last Thursday probably, we showed examples of sometimes not only do the s electrons go away, but sometimes the inner level d electrons are removed when ions are formed as well. So coming back to this formula, if we ask them what the formula is for sodium nitride, its formula would have been Na3N as its formula. Now, one of the ways that your textbook writes these Lewis diagrams is sometimes like this, and there are 2 different ways of writing the same thing. Another way might be to write it as 3Na plus and show the nitride ion like this. So this is another way of writing the same thing. Either one of these 2 ways would be ways to write the Lewis diagram for sodium nitride. To be honest, I don't remember. You should be familiar with both of them. I've actually always been accustomed to writing in this way, and I think this is the way that they appear, this first way. But your author, you're going to notice, likes to do it this way down here. Okay, let's go ahead and you do this one. Let's take aluminum and oxygen. Let's write out the Lewis diagram for a compound comprised of aluminum and oxygen, and then write out its chemical formula. So you can write a Lewis diagram for aluminum oxide, and then write out its chemical formula. Check with another neighbor. Make sure that you're in agreement. While you're doing that, I need to pick up something in the neighboring classroom. Check these out. Okay, any questions on these? Any questions? Going once. We cool in the back row? We okay? Yeah? All right. Let's go on here. Next up, we're going to look at covalent bonding. And as an example, let's look at something like bromine monochloride, BrCl. Now, if we're going to make a model of bromine chloride, we need to first start by writing out Lewis diagrams for each one. So how many valence electrons will the bromine have? 7. Chlorine will have 7 as well. So we'll start with the bromine. 1, 2, 4, 5, 6, 7. And then if we looked at the chlorine, we'd have 1, 2, 3, 4, 5, 6, 7. Then if we want to write out the Lewis diagram for what happens when they form, we can just go ahead and take the chlorine, slide it on over here. And part of the reason why we'd do that is because if we look at the energetics involved with transferring electrons, you might remember as we went back, I don't know if it was last class, here it is, that once we get to something like chlorine and we start taking off one electron, then we take off a second electron, and then a third. There gets to be so much energy by the time we get up to 7 electrons that it becomes energetically impossible to do. So the easier way to do it, rather than giving up electrons, is to share electrons. And so we can take the chlorine, slide it over here, and when we do that, through the sharing, the bromine can still access the 8 valence electrons, and the chlorine can still access the 8 valence electrons. Each one of them here still satisfies the octet rule. This pair of electrons that we have right here, we say is a shared pair. Another name for a shared pair of electrons is a bonding pair. So a shared pair or a bonding pair. Or another term for it is a covalent bond. So these are all terms that we use to describe what this shared pair of electrons is. And what we do then when we write out the Lewis diagram is like this. We write it as Br-Cl, where we represent the shared pair of electrons as a dash right there. So from this point forward, when you're asked to write out a Lewis diagram for compounds that have covalent bonds, shared pairs of electrons are always written in there with a dash between the atoms. Now, if we went to something like H2O, if we wanted to write a Lewis diagram for this, we'd start by looking at where they're located in the periodic table. And oxygen here has how many valence electrons? 6. Hydrogen here has 1 valence electron. So if oxygen has 6 valence electrons, which we can put in as 1, 2, 3, 4, 5, 6, we can then place the hydrogens in here like this, hydrogen and hydrogen, showing where that pair of electrons is shared. Then again, through the sharing of valence electrons, this oxygen can have access to 8 valence electrons. This hydrogen here can have access to 2, and this hydrogen here have access to 2. And of course, when we write it like this, hydrogen would never show an octet. The reason why hydrogen would never show an octet is because of what? Right, the first valence shell, or the first shell there, only holds 2 valence electrons. So when hydrogen fills its outer shell, it is taking on the configuration of helium and would have just those 2 valence electrons. So then when we write out the Lewis diagram for the H2O, we'd show the oxygen, we'd show each line here representing the shared pair of electrons, and then we place the extra dots out here on the oxygen like this. And these pairs of electrons that we have out here on the oxygen, these are not bonded to anything, but one of the things that you're going to notice is that is a difference between when you write out Lewis diagrams for individual elements and for molecules, is that in molecules, electrons are always paired up. So we have them represented like this, which we have the bonding pairs. And out here, we have these, which are referred to as the lone pairs. You know, like this, lone pairs. See, I was trying to go to the other room. I actually have pairs in there, but I forgot to bring my pairs over here today. So I have a couple lone pairs. So I had to show them. See, sorry. Yeah. But we call them lone pairs. So in molecules, we either have a bonding pairs or we have lone pairs. And it's important that we pay attention to these. In chapter 9, we're not going to do a whole lot with the lone pairs other than to remember that to include them. When we get into chapter 10, we're going to start talking about molecular geometry and shapes of molecules. And at that point, then the lone pairs are going to come into play as far as determining molecular shape. All right, so next, if we were to look at the periodic table and we want to show numbers of bonds now that these things make, they work something like this. First of all, if we are in group 7A, these have how many valence electrons? They have 7 valence electrons. Because they need 1 more to complete the outer level, these usually or preferentially will form 1 bond. Elements of group 6A, because they start with 6 valence electrons, need 2 more to complete the outer level. And the usual number of bonds here is 2 bonds. And if we keep going here, group 5A, the normal number of bonds here would be 3 bonds, and group 4A then would have 4 bonds. Okay, now again, this is a normal number. This is not the always number. This is a normal number. We're going to find out here real soon that whatever we talk about as a normal number is going to get thrown out the window. But again, if there's a preferential number of bonds, these would be the preferential number of bonds that they make. So if we came back and we wanted to write out a structure for N2, we could do that. Because nitrogen, coming back here, is in which group? 5A, which means it has 5 valence electrons and will form 3 bonds. So if we come back and look at the structure for a molecule of nitrogen, if we have 2 atoms and each one needs to form 3 bonds, the only way that these can do it would be to form not a double bond, but a triple bond. Yeah, we need a triple bond in here. And then as far as completing the octets, remember now that each line counts as 2 electrons. So if we look around this nitrogen already has access to 6 valence electrons, so it would need 2 more to complete the octet. And then if we look to this other nitrogen is already showing access to 6 valence electrons, so it would need 2 more to complete its outer level, like this. And so at the end, we wind up with each atom in the molecule having 8 valence electrons. Now, when we count up the total number of dots, here, we count 2 here, and then remember each line counts as 2 as well. We have 2, 4, 6, 8, 10 all together. That number 10 should match the number that we'd get from the valence electrons that each atom contributes. So in other words, each nitrogen would contribute 5 valence electrons. We have 2 nitrogens. 2 times 5 gives us 10 altogether. And that should match the 10 that we've shown here in the structure. And it does. And so kind of as a goal, not only do we have to make sure that we satisfy an octet or noble gas configuration for each one, but we have to make sure that the sum of the valence electrons matches the total number that we have shown here in the molecule. So to help us along with that, in your packet, we have a number of rules. And the rules here, again, these pages are whacked out, but we're going to be looking at this whole side right here kind of as a way, if we were to open it up like this, and look at pages 1 and 2, this kind of tells us, and the page numbers are down in the bottom corners here, this is going to tell us then kind of how we go about writing those Lewis diagrams. There's a set of rules that we'll be using. So let's look at some examples and see how we might go about writing out those Lewis symbols. And again, talk about different names here. We're showing Lewis dot structures. So the first thing we're going to do, oh yeah, we need some structures to write out. So let's write out some structures. Ones we are going to do, I know I have them here somewhere. Which ones are we doing? Here we go. We're going to do PCl3. So I'm going to put this in here, PCl3. We're going to do CO2. And then we're going to do the sulfate ion. So we'll try it right here, sulfate ion. Then we'll do phosphoric acid, H3CO4. Then we're going to do the carbonate ion. And then wrap up with nitric acid, HNO3. So these are the structures that we are going to write out Lewis diagrams for. And again, to write these out, we are going to use the rules that are shown right here. So the first rule, we're going to be working with phosphorus trichloride. First step here is to calculate the total number of valence electrons. So coming back to PCl3, let's calculate the sum of the valence electrons. Phosphorus will have how many? 5. Chlorine will have how many? 7. And how many chlorines do we have? 3. So 3 times 7 is going to be 21, plus 5 is going to give us 26. So that means our model should have 26 valence electrons altogether when we're finished. All right, then we go to rule number 2. Rule number 2 says write the skeletal structure connecting every bonded pair of atoms with a pair of dots or a dash. Now, if we're going to write the skeleton structure, we go to the next page, and it tells us how we might predict what that skeleton structure would be. It says, many small molecules or ions consist of a central atom around which are bonded atoms of greater electronegativity. So one of the things that's in your packet, I don't remember where it is, here we go, is this is your other packet, is a table of electronegativity. And again, usually when we write out Lewis structures, the element with the smallest electronegativity goes in the center, and then we surround it with atoms of greater electronegativity. And that's usually the case. So in this case, if we're dealing with and as far as what the electronegativities are, I'll give you a definition right now, but we're probably not going to use this much until we get into chapter 10. So for right now, when we talk about the electronegativity, here's what this is. We say that the electronegativity is a relative measure. It's a relative measure of the attraction an atom places on shared electrons. It's a relative measure of the attraction an atom places on shared electrons. And if we look at the general trends of the electronegativities, just like when we looked at trends before for radii and such, as a general rule, what happens to the electronegativities as we go across from left to right? Values increase. And as we go down within a group, the general trend is that the values will decrease. All right, so again, as a general rule, not the rule, but kind of the general trends again. Go from left to right, the values increase. As we go down within a group, the values will decrease. What this is also saying is that if it's a relative measure of the attraction they place on shared electrons, the element that has the greatest attraction for shared electrons would be fluorine. The element with the least attraction for shared electrons would be francium down here in the opposite corner. So again, fluorine, the greatest attraction for shared electrons, francium, the least attraction for shared electrons. So coming back to this here then, we look at molecules or ions and try to figure out which one goes in the center. We usually pick the one that has the lowest electronegativity and put it in the middle. Secondly, if we have molecules or polyatomic ions with multiple atoms of each element, these here often have symmetrical structures. This should have read S2Cl2, not SCl2, but S2Cl2. So what this means then is if we draw out a diagram for this, we put the two sulfurs in the middle, and then the chlorines on sides opposite of them. Something like P2Br4 would be shown where we'd put the two phosphorus in the middle, and then the bromines on opposite sides. So again, as you're trying to draw these out, we often want to think about symmetry in developing those structures. Next refers to oxoacids, or your text calls them oxyacids. What these consist of is that we have an atom of low electronegativity surrounded by oxygen, and then outside of the oxygen we have one or more hydrogen atoms. So in the oxyacids or oxoacids here, the hydrogen is directly bonded to the oxygen, not to the central atom. And then finally it says of several possible structural formulas, the one that has the atoms giving their usual number of bonds is the one that is preferred. So sometimes we can come up with multiple ways to write a structure. We can wind up with a structure where they have their usual number of bonds, which is what we were showing right here. Then that would be the preferred structure that we wind up with. So in this case, in PCl3, if we want to write the skeletal structure, which element is going to go in the middle? P will go in the middle. And then we'd surround the P with Cl. And so it looks something like this. Once we place these around, we then ask ourselves, how many valence electrons have we already used up? We've used up 6 because remember each line stands for 2. So we have 26 minus 6, which is going to leave us 20. Then the next rule says we're going to distribute the electrons to the atoms surrounding the central atom or atoms satisfying the octet rule. So we don't assign them to the central atom first, we assign them to the other ones. So we assign them to the chlorine. And again, we assign them as pairs. So you put them in 2, 4, 6, 8, 10, 12, 14, 16, 18. We just used up 18. That means we have 2 left to go. And then reading the instructions, tells us what we do with those. It says distribute the remaining electrons as pairs to the central atom or atoms, shifting pairs of electrons from the surrounding atoms to the central atom if multiple bonding is necessary for the octet rule. Well, this one's easy. We simply take those two that we have left, put them here on the phosphorus, used up those two, we've got 0 left. And of course, once you've done this, we've already confirmed that we've put 26 dots in there. You should then go back and just reconfirm that you have an octet available to each of the atoms in the molecule. So any questions on this one here? Okay, let's try carbon dioxide, CO2. Again, we're going to follow the steps. We'll follow them sequentially. So the first thing we're going to do is to write or calculate the total number of valency electrons. So in CO2, carbon's going to have how many? Each oxygen will have how many? 6. And again, that comes from their position on the periodic table. 4 here, 6 here. We sum these together, we wind up with 16. And the next step is to write the skeletal structure, connecting every bonded pair of atoms with a pair of dots or a dash. We want the atom of lowest electronegativity in the center. So which element goes in the middle? Carbon will, right. So if it's carbon in the middle, surrounded by the oxygens. At this point, how many electrons have we used up? 4, which means we have 12 left to go. So then the next rule says we're going to distribute the electrons to the atoms surrounding the central atom or atoms satisfying the octet rule. So we put in 2, 4, 6, 8, 10, 12. That uses up all 12, so we have 0 left to go. What's wrong with the structure? Right, carbon does not have the octet. It only has available to it 4 electrons. So then we need to do the double bond. So our next step here says that we distribute the remaining ones to the central atom. Well, we don't have any remaining. So the next part then is to shift pairs of electrons from the surrounding atoms to the central atom if multiple bonding is necessary for the octet rule. So we get rid of 2 here, 2 here, put them in here as double bond. At this point then, every atom has satisfied the octet. We have 8 available to this oxygen, we have 8 available to this oxygen, and we have 8 available now to this carbon. Now, one thing that sometimes I'll see answers like this, and let's see if you can tell me what's wrong with this way. What's wrong with writing them like this? We still have an octet here and an octet here, but what's wrong with it? Right, the electrons aren't paired. So we need to think about, if it helps you, think about your pairs. All right, remember that electrons are always paired up in molecules. Now, whether you write the pairs like this or write them like this, it doesn't really matter where you put them. Sometimes, even when we write them like this, sometimes students will show it like this to kind of more reflect how they'd be in three-dimensional space. But we haven't talked about electron pair geometry or molecular geometry yet, so you wouldn't know to do that at this point. So again, putting them in at this point, as long as they're paired up, that's what we pay attention to. Any questions on this one? Yes.
I'm still a little confused why carbon 4, because I thought there's only 4 valence electrons, but there's 4 lines.
Right. Okay, so carbon will ordinarily form 4 bonds because it has 4 valence electrons. And one of the things that might help you is like this. If I draw this a little bit more uniformly, remember each line represents how many electrons? 2. So if it would help, you could think of the ones that came from the carbon as being on this end, and then the ones from the oxygen being here on the other ends. Okay, so you can kind of think of them like this. So because carbon has the 4 valence electrons, it still needs those 4 more to fill the outer level, which means it's ordinarily going to form 4 bonds because it needs 4 more to complete that level. That's what it boils down to. And oxygen, because it starts with 6 valence electrons, that's what these 6 are showing right here, needs 2 more to complete the outer level, so it can use the 2 extras from the carbon to complete its outer level as well. Yeah, got that? Yeah, so sometimes then, like I say, what will help you, just think of there actually being dots on the end of it. And if you want to even color code them in like I do, that will help you kind of do an accounting of where exactly they came from at the beginning. Okay, anybody else? All right, let's do the sulfate ion. Let's do the sulfate ion. On the sulfate ion, we sum up the valence electrons. Sulfur has how many? 6. How many for each oxygen? 6 as well. So we have 6 from the sulfur, and we have 6 for each oxygen. There's 4 oxygens altogether. And what does a 2 negative charge mean? 2 more electrons. So we need to add 2 more. So altogether we're going to have 32. So then writing out the Lewis diagram, we need to figure out which element goes in the middle. Sulfur will go in the middle, good. So we put the sulfur in right here in the center. And then we're going to surround the sulfur with 4 oxygen right here. So now in this process, how many valence electrons have we used up? 8 valence electrons. So since we've used up 8, that means we're going to take 32 minus 8. And 32 minus 8 is going to leave us with 24. Next step says we're going to distribute the electrons to the surrounding atoms. So we come back in here, we put in 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We've used up all 24. We have none left to go. We take a quick check on sulfur, and is sulfur satisfying the octet rule? It is. So we've satisfied the octet rule for all of them. There's only one thing left to make this technically correct, and that would be square brackets. So somewhere in the structure we have 2 extra electrons. We'll put square brackets around the entire structure, and then we charge 2 minus outside. Any questions on this one? Okay, let's do phosphoric acid. Now, phosphoric acid is going to be one that when it talks about oxyacids right here and doing the skeleton structure, says oxyacids. What happened to that page? Here we go. Oxyacids have oxygen atoms bonded to a central atom, and then the hydrogens are bonded to the oxygens themselves. So which element are we going to put in the center on this one? Phosphorus goes in first. What are we going to surround the phosphorus with? Oxygens. How many oxygens? 4. And then we have hydrogens. Where do we put the hydrogens? On the oxygens, right. So we do something like this right here. So now when it comes to determining valence electrons, we need to find what that sum of the valence electrons is. So let's go ahead and do that. Each hydrogen has how many? 1. And we have 3 hydrogens. Phosphorus has how many? 5. So we put in 5 for the phosphorus. Oxygen has how many? 6. And how many oxygens do we have? 4. So we now sum these together. We have 3 plus 5, which is 8, plus 24, which is going to give us 32. And if we look at our structure, how many have we used up? 6, 8, 10, 12, 14 we've used up. Okay, remember that each line counts as 2. So we've used up 14 already, which means we have 18 left to go. So now the next rule says we're going to place the dots on the surrounding atoms. Are we going to put dots, any more dots around the hydrogens? No. So we're going to just put them on the oxygens. So we put in 2, 4, 6, 8, 10, 12, 14, 16, 18. It uses up all 18. We've got none left to go. We do a quick check on the phosphorus, and phosphorus will need. All right, we're good. All right, you do the last 2 here. Do the carbonate and the nitric acid. Follow your rules and see what you come up with. Okay, guide me. Which one for the carbonate? Which element goes in the center? Carbon. Surrounded by 3 oxygens. 1, 2, 3. Of course, this uses up 6, which means we have 18 left. Where do the next dots go? On the oxygens. We put in 2, 4, 6, 8, 10, 12, 14, 16, 18. We've used up all 18. Do we have octets for everything? No. So what do we need to do? And how do we double bond? And we take 2 away from one of the oxygens, place it in here, and that would give us the correct structure. We're missing one thing yet, and that is brackets. So we're going to put square brackets around this one here. And outside of the square brackets would put 2 minus to show that there's 2 extra electrons in that structure. Mastering chemistry, I think I mentioned this already, doesn't handle brackets. So if you put it in, you're just going to put that charge on in there somewhere, but the brackets won't show up. Okay, any questions? Okay, nitric acid, which element in the center? Nitrogen. And surrounding the nitrogen, we would have 3 oxygens. How about the hydrogen? Where does that go? It gets stuck to one of the oxygens. It does not go on the nitrogen. So which oxygen you attach it to doesn't really matter. When we start looking at molecular geometries in chapter 10, we're going to find out that it doesn't matter a whole lot. We are going to find out, though, this is not a today thing. You want to wait till after Thanksgiving for this. But we're going to find out, like on this one here, you might say, well, how come we took the double bond off the top one? How come we didn't put a double bond in on this one? But that's a whole nother thing. We can wait for that big surprise after Christmas. Not Christmas, Thanksgiving. There we go. Christmas, you'd love that, wouldn't you? Okay, so, but we put the hydrogen in here. And from here now, we're going to, let's see, how many do we use up? 8, which means we've got 16 left to go. And where do these go? On the oxygens. So we put in 2, 4, 6, 8, 10, 12, 14, 16, Oh no, what's next? Yeah, so we need to take one of these off of here and put it in as a double bond. And again, this is an after Thanksgiving thing. We might say, well, why did we take it off of this one? And why didn't we put it here? We can learn that surprise next Tuesday when we come back. Do we need square brackets on this one? No, we don't. And this then winds up being the structure for HNO3. Again, you could have had the hydrogen positioned at any one of these spots, and the double bond could have been at any one of the oxygens, just not on the one here to which the hydrogen is attached. Okay, any questions? All right, last thing for today here, and I don't know why these pages are so whacked out, but if you flip over, the very top one appears to be exceptions to the octet rule. We're going to look at some exceptions to the octet rule, and we're going to deal with them on these examples. They are BF3, then XE, F4, and then the last one is going to be NO. No. Okay, so come back here, we got BF3. Now, if we look at the exceptions to the octet rule, right here, those molecules and ions with an odd number of electrons in their Lewis structures are referred to as free radicals or simply radicals. And a couple examples of those would be NO and NO2. And we're going to look at NO here today. Then, these elements are ones that can form less than a complete octet. They are beryllium, boron, aluminum, gallium, germanium, indium, and tin. If we look at where they are located in the periodic table, we'd see that their location, these right over here, we have beryllium, boron, aluminum. What else do we say? Gallium, germanium, indium, and tin. So these here are ones that can form less than a stable octet. Then over here, we have phosphorus, sulfur, chlorine, krypton, and all of the elements below them will often form more than a stable octet. So, and if we look at them on the periodic table, it's these right here, and everything below them may form more than a stable octet. Now, any ideas, first of all, why these might form more than a stable octet? And why I say something like nitrogen, oxygen, fluorine couldn't? Well, that's a chapter 10 thing. But if we were to talk about it right now, we'll find out that it has to do with D subshells. You might remember in period 2 only has S and P subshells. We don't see D subshells available until the third energy level. And so it turns out that once we get into the third energy level, we have those empty D subshells available. Those D subshells are sometimes used in bonding, and that's how we wind up exceeding the octet rule, is because those D subshells are used. And they can't be used here for those in the second energy level because the D subshells don't exist in the second energy level. So for right now, just know the rules and the exceptions. And then chapter 10, which is after our fourth exam, will be more of the explanation why. So to write these out, we come back here to the BF3. Boron, of course, is one that can have less than a stable octet. So if we're going to place an element in the center, the one that's going to go in the middle is going to be boron. So we put the B in the middle. We surround the boron with the 3 fluorine atoms. And then we calculate that sum of the valence electrons. So to calculate that sum of the valence electrons, boron has how many? I hear 5, 8, what is it? 3, right. So it has 3 valence electrons. Each fluorine has how many? 7. And we have 3 fluorine atoms. So altogether we'd have to count for 24 electrons. Is that right? Seems like a lot. Okay. So we come back here, and how many have we used up at this stage? 6, which means we have 18 left to go. So now, which elements do the dots get assigned to? Fluorine. So we put in 2, 4, 6, 8, 10, 12, 14, 16, 18. At this point, we've used up all the valence electrons. And then what about boron? Yeah, we're good. Boron can have less than a stable octet. It's one of those elements here that can have less than a stable octet. And so we would leave it then as is for this compound. Next up, let's do xenon tetrafluoride. Xenon would have how many valence electrons? 8. So have 8 valence electrons. Each fluorine would have how many? 7. And we have 4 fluorine atoms. 4 times 7 is 28. Plus 8 more gives us 36. Which element goes in the center? Xenon will. And then we surround the xenon with fluorine. At this point, how many valence electrons have we used up? 8, which means we've got 28 left to go. Then we start putting in dots as pairs. Where do the dots go? The fluorine. So put in 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We used up 24, which means we've got 4 left to go. So where do the remaining 4 dots go? They will not double bond. Xenon can have more than 8, but fluorine cannot. Okay, so xenon is one of them that is capable of having more than a stable octet. And if we kind of follow our rules through here, it tells us that whatever we have left, we distribute them as pairs to the central atom or atoms. So again, if we follow through the sequence here, what we do is we assign them as pairs to the central atom. So put in 2 here and 2 here. Again, remembering that they are always paired up. Any questions on this one? Okay, then the last one is the nitric oxide or nitrogen monoxide. Calculate the sum of the valence electrons. Nitrogen has 5, oxygen has 6. Altogether we've got 11 valence electrons. So now the central atom in this case, so there's really only 2, so nitrogen would be central, so to speak, but would attach it to the oxygen. At this point we've used up 2 valence electrons, which means we've got 9 left. Now nitrogen again is the atom of lower electronegativity, so even though there's only 2, we consider it to be the central atom. So that means that the next electrons get assigned to oxygen. Put in 2, 4, 6. This uses up 6, we're left with 3. And at this point then, we would go to the nitrogen and we put in 2 and 3. We've used them all up. We don't have any left to go. And then we say we're going to wind up being happy with this one because nitrogen is one of those that will often wind up forming what's called a free radical. And on a free radical, we have an odd number of electrons. There's no way we can wind up showing and octet. So with that, this is it for today. Anybody have any questions? Okay, the handouts for today that we passed out, these are for the rest of the semester. They're for the rest of the semester. These are chapters 9 and 10. So we will not cover all of this before this exam. This is chapters 9 and 10, the handouts for today. That's it.